Okay, so we're in the air. Alright. Good afternoon or whatever time it is in the place. My name is Bernardos and welcome back, I guess. As I've said on the previous week, this week we'll learn about about pointers. Yeah, about pointers usage. I said that I would create a CLI, but in the end I have no time, so here we are. This GitHub issue in my engineering roadmap is basically a screenshot, you can say, about what I did throughout the week. Lately, I also said that I would try to create a comment about database, but in the end I have no time as today is already Saturday of January 31st. So without further ado, let's get started. So what is a pointer? This is on the day one. Okay, so pointer is basically a variable that holds the address of another variable. We are able to read or modify the value inside the address via the reference. So this is a snippet that I make. Let's paste it into a C file and type gcc output main.c main. So what did we do here to get the value of 8? So we create a variable called number, and we create a pointer variable that points to the address of 8. So the p_number variable stores the address of number, and when we want to print that into the standard std_out, we dereference the p_number. So what about the syntax here? The asterisk or star in the initialization of the variable is used to declare that this is a pointer, and the ampersand is used to get the address of a variable. Meanwhile, when we want to print, we dereference the pointer number, which means go to the address and get the value inside. So that's why it prints 8. So before we continue further into pointer, we need to know what is RAM and CPU. RAM operates on the same language as the CPU, as it suggests, binary 0 and 1. It is a contiguous block of zeros and 1, or binary, 0 for not being flowed by electricity and 1 for the opposite. However, the CPU interprets them as 1 byte, so the CPU doesn't map them 0, 0, 1, 1. Instead, it groups them into 8 bits, which is 1 byte. So like an address is a collection of 0 and 1. Something like that. Okay. So what is actually a variable? We said that a pointer is a variable that stores the address of another variable. But what is a variable? A variable is basically a box that acts as its value. So when I have a variable called number, it acts like it is as if it's the number 8. So we have int integer x equals 5. X behaves as if it is 5, as I said. Now, as we talk about, RAM can only store binaries. So how can we have letters like A or B? How can we do this? The integer 1 character, this will print, and it prints 98 because B converts to 98, as you can see. Float, so if in RAM it is only binary 0 and 1s, how can we have a floating number? So the answer is IEEE 754 standard. The first bit in the binaries determines the positive or negative. The exponent determines how much to the right the point is. So where is the point is located, and the mantissa is as the number, so the rest of the binaries. Double is 8 bytes, which is the float with more precision with double the memories, as you can see, 4 and 8. Void is 0 byte. It holds no memory in RAM, and you can't even assign a variable with the type void. If I'm not mistaken, this is not allowed. Yes, incomplete type void is not allowed. So why do we even use void type? Later it will be explained down the line. But for now, for the types that is larger than 1 byte, they live contiguously. As I said, 1 byte. So when you print the address of a number, sorry. When you print the address of a number, it is 1 byte. But as we know, an integer is 4 bytes. So what does this address mean? It means the start of the address. So this is not the entirety of the address. It is the first address in which the byte lives, the value lives. 4 bytes mean 4 contiguous bytes next to each other. And as a side note, void cannot be used as a variable type, as I said. It can be used as a function return type and a void pointer, which we'll discuss later, which is a generic placeholder for a pointer. Now, we talked about the primitives: integer, character, float, double, void, and pointer. Now we move to array, string, and struct. Just as I said before, any type of data lives contiguously next to each other. The same with array and struct, and I forgot to say it, string. An array is a box that holds the same type of variable. An array, variables live next to each other. So let's say I have this variable, right? For variable, I have 1, 2, 3, 4. This will return 0. So when I print f the address of, don't use the ampersand to get the address, because arrays decay. What does decay mean? It will be explained later down the line, but for now, number gets the first address of the value. So say first, don't forget. Now, what does this address mean? It means the address of the first value. However, an integer is 4 bytes, so this is the starting address of the first value of. So let me explain. So when we do this, this gets the address of the first value of the array. And since the first address of the array is an integer, which is 4 bytes, it gets the first byte of the first value of the array. So this is the address of the first byte of the number 1. So what about struct? A struct is just a box collection that holds many types of variables. The same with array, the variables live next to each other. So let's say for this example, this struct, I'll just copy this one. I'm too lazy. Now char name, which is usually called string, lives contiguously next to each other. So this struct size is 104. Let's prove that. Okay, when f is it, this is not an int, this should be long variable, but in my theory it should crash. This provide an argument. Okay, this is maybe too big, too large for its type. This provide an argument. So wait, bro. It's still too big. Long. Is it long int or long? I forget. This doesn't happen, so okay. Just as a side note, this is to prevent the stack overflow bug, which if in a stack memory it is limited, so you need to put a big variable on the heap to make sure there is no stack overflow. I don't know what happened just now, but that's the theory. I don't know about that in practice, but so the next use case of pointer is accessing the memory of a manager. So in a specific case where you open a file like a txt file, we gain the address of the struct. So file pointer. This we get the address of a quote-unquote manager. This is specifically used for inputting and outputting or writing to a file. We won't dive deeper into this, but as you know, a pointer is an address holder, so we get the address of a manager. So now the syntax. What is the ampersand, asterisk, and point symbols? Yes, point symbols is that. The ampersand, as I said before, means get the address of a variable. And now the asterisk. For initialization, the integer p number asterisk p number equals ampersand number. This marks that this variable is a pointer, as I said. When dereferencing asterisk p number, this means go to the address and get the value inside that address. Also, you can change the value when dereferencing. P number equals 28. This will result in the number's value being changed. So this means go to the address and change the value inside. So what's the point symbol used for? This is used for structure access. So this is specifically used with struct, a collection of data. Some struct point value is the same as dereference the struct and get the value. So that's what I learned in day 1 about pointers. We barely scratched the surface. This is just the theory. And in day 2, we learn about the danger of pointer. So this is what I said before, array decays. As we talked about in the previous issue, one of the primary usages of a pointer is pass by reference. So in C, to enable passing an array to a function, the compiler automatically does an explicit conversion from an array to the pointer of the first value. This is useful for passing by reference. However, it results in losing the ability to check the size of the array inside the function. So this is why in a function, you usually also pass the size of the array. So let's pass this code right here. So from my comments, we see the void print size. This will return 4 or 8 depending on the architecture, always guaranteed. An integer number, we create an array of number size 4. So as I said, not as I said, but array decaying happens most of the time, except for some function like size of and other functions. I forget all of them. I forget what are they, but the only one I remember is size of. This will print the real size of the array, not the size of the pointer. And we pass the pointer, we pass the array to the function. This is not the array. This will just pass the address of the first value of the array. Will print 4 or 8 no matter what. And we create a pointer to a number. As I said, this decays to the address of the first element in the array. So this will print 4 or 8 no matter what. Okay, oh, I forgot to save. Oh shit, what the hell? Oh, this is the warning you get from the compiler that this will decay. This array will decay right here. But as what I said is true. Size of the array is 40, and passing it to a function will just print the size of the pointer, which is 8 in my architecture, and the size of pointer is 8. So now we are entering pointer arithmetic. The C compiler may optimize our source code into something what we don't expect sometimes, but it's actually pretty smart. Pointer arithmetic means that when you do an arithmetic operation excluding multiplication and division, since in memory that doesn't mean anything, the pointer doesn't move 1 byte, as I explained. It moves the size of the pointer. It moves the size of the value upwards. And from the array decay previously, in the real software, people pass the address of the first element via decay and the size of the array to do pointer arithmetic. Yes, let's pass this code right here. So let me explain my code right here. This loop through the array. We got the address of the first element of the array and the size of the array. So we loop through the first address of the array, go up 1 element in the array. It's the same as the now accessing an index using array inside a, I don't know what is this called, but let's call it a box. With E, it converts this inside a box into the reference, the array address plus 1. This is the example of pointer arithmetic. Instead of going 1 byte, it goes the size of the type, like explained right here. Alright, so I have an array of numbers, and we create a pointer to the first value of the array, and then we print the value of the first. We print the value of the first. We print the value of the first value in the array. So this is why we need to pass the type here and the value of the variable. Now it's the pointer that cannot be changed. You can change the value of the variable, but you cannot make pointer point to another variable. Address of variable. Now this is not allowed. Expression must be a modifiable value. So this is a constant pointer. This is constantly pointing to a variable. So you cannot change it. Now we have a constant pointer to a constant. This means both the pointer and the variable it points to is constant. So you can only do reading and not writing. Neither the value nor the variable in which the pointer holds can change, nor the address in which the pointer holds. Sorry. Okay, so let's paste this code right here. We create a constant integer. We create a pointer to a constant. Yes, a pointer to a constant, and we can output it as I said. But you cannot change the value. It is invalid. I don't know what does this happen. I think I have the better comment on, so bear with me, right? We have number 2, number 3. This forever points to the number 1, a constant pointer. We are allowed to modify the value of the variable it points to, but we cannot change what address does the pointer holds. This is invalid since pointer number 2 is a constant pointer. Now, in the end, we have a constant pointer to a constant. Neither the pointer nor the variable it points to can change. This is invalid since we cannot change the value of a constant, and this is invalid because we cannot change the address in which a constant pointer holds. Yeah, my English is getting better. Alright. Void pointer. Void pointer is a pointer that points to a void type. Void type doesn't have memory or bytes. Its primary usage is a generic placeholder, as I said in this main as seen in these main pages. Malloc is void type, void pointer. Calloc is void pointer, realloc is void pointer, real array is void pointer. I don't really know about calloc, realloc, or realloc array, but let's just talk about malloc and free. So let's pass this function, this code right here. We have a struct called person with the size of 104, 100 for string and 4 for age. We create an instance of that struct with my name, Bernardus, with the age of 15, and we create a pointer to that value. We create a pointer. We allocate a memory for Bernard for a person instance. Malloc is implicitly cast. So as I said earlier, void pointer is a generic placeholder. So this void pointer can be cast into other type, which can be casted into a person type. So this will give us another memory in which the size of a person, which is 104. We free it to avoid memory leak. And then this is the same as the above. The compiler automatically behind the scene casted the type of void pointer into person pointer. In C++, this is not allowed. You must explicitly cast it. However, in C, the compiler automatically does this for you. This is explicit, and this is the same. This will print nothing since I use no printf, but you got the explanation. So now we have finished since we now have finished day 2, let's move to day 3. And somehow I forgot to copy the documentation of day 3. We can do it from here, but I want my Obsidian nodes to be perfect. So sorry for the information, guys, and let's go back into day 3, which is C++. Documentation of pointer in C, day 3. Shalom. I have slept and I have woken up, so now time to learn about pointers in C++. We go to main.cpp. C with classes. Yes, C++ used to be called C with classes. It's historical fact, but I won't dive deeper into historical fact. Was in its early day an extension of C. So every valid C program is a valid C++ program, and manual pointers still exist in C++. So what does this code do? We have a manual pointer, and we can print f8 or using the C++ way of printing a value to the standard output, which is cout. These coexist. So C++ is a superset of C. So every valid C program, you can put it into a CPP extension and it will still compile. The compiler changed. Now it's G++. We output the main.cpp and main. Now this is what I said earlier. In C++, you must explicitly cast malloc into your type, as we see here, and we must cast the void pointer into an integer pointer before we can use it. In C++, new does 3 things. Allocate memory, immediately place the value there, and returns the address there. So you won't have a null pointer or uninitialized pointer, that is not uninitialized. You won't have an empty pointer. Every pointer will have a value. So this just showcases that manual pointer still exists in C++, printf can coexist with cout, malloc and free can coexist with new and delete. So next we have a new friend, RAII. Okay, and our new friends, unique pointer, shared pointer, and reference. To avoid the danger of pointer, raw pointer, C++ introduces this thing. I used new keywords in the previous example. It does the same thing as malloc, but you immediately place the value in the allocated memory, but you still have to delete the memory, otherwise memory leak. Now here's what RAII and our 4 friends enter the scene. Resource acquisition is initialization. Before we go deeper, we need to understand that most of the stuff inside the std namespace is functions, const or values, and classes. C with classes. RAII is basically create a pointer in the stack, go to the heap, allocate the memory there, and when it goes out of scope, it calls the destructor, which deletes the memory on the heap before finally going out of scope. Let's paste this one. Now what does unique pointer does? It creates a pointer to an object on the heap. So the integer, the value, lives on the heap, but the object of unique pointer lives on the stack. So as we know, in the OOP world, which I love, every object has constructor, yes, constructor and destructor. The constructor triggers when the object is created, which the constructor will allocate the memory on the heap, and on the destructor, when the object goes out of scope or is destroyed, it will free the memory on the heap. So before reaching here, the unique pointer calls the destructor to remove the memory in the heap before going out of scope. So that's about memory, and now we have a unique pointer. A unique pointer is an object class that points to an object, and one value can have one pointer, one owner. So I have a struct human right here. This is the constructor of the struct human. This is needed somehow, so I don't know. We create a unique pointer with the new keyword called Adam, who has the title of the first human, and we go to the address of the new human and get the value of the name. This is the method way of getting a value. However, as I said, every valid C program is a valid C++ program. So this we perform operator overloading. Unique pointer is an object, hence you can't directly dereference a pointer. Yet this is the case of operator overloading wrapper. So whenever you dereference something, it will trigger the operator overloading. Every time you dereference a pointer, it calls a function that returns the address of the value and dereferences it. This is so that every C program is compatible with a C++ one. This is also works since this is the same with this. And unique pointer, this is invalid. You cannot do this. One value can only have one owner. You need to move the ownership. So what do I mean by that? The Adam instance of human has the value of the first human and 15. So when we try to copy paste the value into Steve, it is not allowed, since unique pointer, as its name suggests, means one value can only have one owner. So in this instance, we move the value of Adam, which is the title of the first human and 15, to Steve. Hence, you cannot use Adam anymore. It is empty since the value has been moved to Steve. Make unique. This is also another way, like how should I say? Modern way of doing things. You don't use the new keyword, Instead, you use the make unique. So you don't need to manually free it later, manually delete, if I make correct. Make unique is the preferred way to make a unique pointer as it's shorter and safer. But I'm not diving deep into this during my C++ time, because I remembered when I was learning about this, the next day was an ELPC competition. Trial, may I correct, but still, out of scope immediately drops. This is where the resource acquisition is initialization comes in. So now we have shared pointer. Now if a unique pointer, one value can only have one owner, a shared pointer, as its name suggests, means one value has many owners. Let's pass this one. We create a shared pointer using the preferred way, and then we copy the value of the first pointer into the second pointer. So both of these pointer points to the same value on the heap, which is 100. This method prints the how many pointer are pointing to this value, returns the number of owners pointer have. We print the address of the first pointer and second pointer, which is the same, if I made correct, and then we print both the value. At this line, both the first pointer and second pointer goes out of scope. So the counter for the object on the heap, for the pointer for the value on the heap goes to 0, which then automatically destroy the value on the heap. Now this prints the same address and returns the same value. Really nice. So just as a side note, shared pointer means many pointer can point to one value on the heap. A bit of a side note, shared pointers also use resource acquisition is initialization. But the difference is that there's a counter on the heap. The destructor doesn't mean destroy the value, rather reduce or decrement the number of owners sharing the pointer. So until the counter hits 0, the value can live on the heap. I'm not gonna deep dive into this as this is a C series. C++ RAII can take so long to understand. So we've talked about pointers, but now this is the modern way of doing things in C++. Reference. C++ reference is similar to that of Rust, but reference is basically another alias or nickname to a variable, allowing you to change the value of a variable without poking at the memory directly. Primarily used in pass-by reference function with one note. The difference to a pointer is a pointer can be null or empty, and a reference must be initialized when it's created, so it must have a value. You can't have integer reference of ref on its own. Yes. So what does this code do? We accept a reference to an integer and we pass in the desired value. It will change the integer value. So this means go to this address and change the value there. The same as pointer, but safer since it can be empty. We have a variable called x which has the value of 8. We print the value, then we modify the value. We pass the variable into the modified value, and we get the reference to x, so we can directly change the value. As you can see, I forgot to remove this for sake. Yes, I was sick when I was doing this, but as I said, malloc sleep time is the best. Okay, now we got into day 4. This is a 5 days, so this is quite long. I have so much. Oh my god. Shalom, I've returned from competitive programming hell. Now time to learn Rust pointer, which was yesterday. In Rust, one value has one owner. This is implemented to prevent data races where many pointers can change a single piece of data. So let's go to, this is my Rust project. This is my Rust project I initialized for this video, for this documentation. Excuse me, I need to drink. Now, ownership. One value has one owner, like unique pointer. In Rust, one value has one owner. This is implemented to prevent data races. Oh, this is placeholder. Oh my lord. We go to source main.rs and paste it there. Rust analyzer does cargo check. Excuse me again, alright? Now, what does this code do? We have a variable called x. It is integer 32 bits with the value of 8. Now, primitives like boolean, integer, float has copy traits, so their value won't get moved. Instead, it will be copied. So this doesn't mean the value would be moved to y, but instead it copies the 8 into this. So x is still valid and y is valid, but however, for variables which doesn't have the copy trait, like a struct, this won't copy, but instead it will move the ownership of the value. So we have a variable named Adam, which is the struct human type, with the title of the first human with the age of 18. I don't know why I put it like that. We print the title and age of Adam, and then we move the value of the first human and the age to Steve. This time Adam has string which has no copy trait. So a bit of a correction from earlier. Struct, I'm not really sure about that one, but string has no copy trait, so the ownership is moved. And then print line Adam's title. This is not allowed. The ownership of the value has moved to Steve, and now Steve has the title of the first human. Why the string object has no copy trait? Wait. Now, this is, as a side note, Rust string is quite similar to that of C++. It's a pointer to a heap object. So why the string has no copy trait, it will be explained later. But if we do want to clone the value, we have to use the .clone method. String is an object, so it has a method. We have Adam again, a human with the title of human, age of 18, create a human named Adam, and then we clone the value of Adam into Eve. So Eve has the title of human and age of 18. Adam is a human with the age of 18, and his partner Eve is a human and her age is the same as Adam. So let's do cargo run. I forget to do this with the two previous example. My bad, I'm sorry. As you can see, this prints and checks out. So we go to the earlier side note. So let's pass this code right here. Now, this creates an object of string consisting of a pointer. A string is basically an object with a pointer to the value on the heap. Same with C++. We have the object on the basically an object on the stack, and it points to a value on the heap. And the string also has the length, stores the length, hence my nickname.length, and the capacity, how much memory was allocated or used for the object. Let nickname string name, so this basically moves the ownership of the name of the value Bernardus to the nickname. This is invalid because if Rust copies the whole object, the pointer which points to the value on the heap will be copied as well. And when both goes out of scope, both will call free. Classic double free security error. And then we print the value, and then we print the address of the address is stored inside the object, and then we print the length and the capacity, which is the size of the object on the heap. This time it creates a brand new object. So this is also why we can do clone with earlier Adam and Eve example, because if we do .clone to a string, this time it creates a brand new object, not copies the whole thing, but creates a brand new object with a new pointer and a new memory. The only thing that will be copied are length and capacity. So this is a valid code, and it checks out. It prints 9 bytes. Now we go to number 2. Rust has no real pointers. So in safe Rust, there is no way to poke the address directly, but we have the bread and butter of Rust, ownership and borrowing. We've covered the ownership already, but now we'll cover the borrowing. It's where you can reference a variable, then reference it to either read only or change the value. Paste it right here. So in Rust we have type inference, which is appreciated. Now we create a reference to the number. I called it pointer number, but this is not actually a pointer. P number is a pointer, or more precisely, a reference to the number. We print the value of the number. We print the value of the number, and then we print the address of the number. And this line is a unique case. Now this is nice printing. Go to the address stored in the number and see what's inside. Rust compiler, I don't know if it's the compiler, but Rust directly, if Rust sees you trying to print a pointer without the :p tag inside the macro, it will go to the address and prints the value instead. So this is explicit the referencing of the pointer. So next one. We create a second number with the value of 7, and then we create a reference to the second number, an immutable read-only reference. You can change where the reference points to. Oh yes, so this is an immutable read-only reference. You cannot change the value of second number as it is immutable reference. Now this one, you can have as many immutable references as possible, and this time we have an let mute third p second number. We get the address of number, an immutable reference that can change who it points to. So this is like so we know that if you only declare a variable with let without mod, which marks the immutable variable, it cannot be changed. Hence, this pointer, it cannot change who it points to, as it has no mute keyword. But this line, it has mute keywords. So this reference can change who it points to. It can change. This is allowed. So this prints the value, this prints the address, this prints the address, this prints the address, which all points to the same thing. Now let's go to below. Now this is about with mutable reference. We create a mutable variable which can be changed. We create a mutable reference, but the reference itself is immutable. It's a mutable reference of value 8 to the pointer third number. This is not allowed because when you print the third number, it's actually passing a immutable reference, and there's only infinite immutable references or one mutable references. You cannot have both, only one. This is not allowed. Typo, not allowed. Let's see p third number. Only infinite immutable reference or one mutable references. Yes. Now go to the address of the third number and change what's inside. This prints the what's inside the address of the third number. This prints the address. This explicit the referencing. So now we have this one. We directly prints the third number, which means passing a mutable reference. Why is this allowed? In older Rust, this would fail. But in modern Rust, the compiler automatically drops borrowing when it's not used anymore. And this one is the same as above. You can have another reference since it's already been dropped. Now, what about pass by, say, how long has this been? Oh my god, 45 minutes. Alright, sorry for the intercession. Now, we have pass by reference, so we've seen the word reference over and over, but we haven't tapped into the real use of pointer, pass by reference. So we have this one. This passes the reference of a human, which means we don't copy the whole value. Instead, we have the reference to the variable, to the human. Create a human named Adam with the title human, clone the value from Adam, and then pass in an immutable reference to the function, which will print the name of title and age of the human, and we have an immutable reference for Eve, and then we change the name to Eve. Since it copies from Adam, her name won't be Eve, so we change the name to Eve, and then we print her value. Save, do cargo run. It's still cargo checking, so let me drink for a bit. This video is already long enough, so I'm probably gonna split it into two videos. I don't know, maybe I still have juice left, so let's go. This correctly prints everything. So, okay, what is this derived clone do? This allows a complex data structure like struct to be copied, as it's not usually allowed, and the rest I've explained it. Now, a quote-unquote raw pointer in Rust. So now we have seen ownership and borrowing. Why bother with a pointer? We have three answers. Foreign function interface. When your Rust code needs to interact with unsafe languages like C, Rust cannot guarantee a C pointer won't be null, hence unsafe pointer. A kernel. In Rust, you can cache a memory address, so you need an unsafe pointer. So, Linux Rust, man. I don't know. Performance. Sometimes the borrow checker is too strict for complex data types, so the developer skips this using unsafe. This is not really performance, but rather a piece of mind to prevent fighting the borrow checker. So now we have a mutable reference. We have a constant pointer and a mutable pointer. Dereferencing is not allowed in safe Rust since it is unsafe and it can be null. Oh my god. I don't know why dereferencing is unsafe, but wait, let me think for a bit. Alright, creating a raw pointer is safe. We just cast a reference to a raw pointer using as. So this instance R1 is a constant point. It's a constant pointer. This is a reference to num as a constant pointer E32. And this time is a mutable pointer. Dereferencing is unsafe. So let's just print this one. Value here raw pointer. Alright. So this both points to the same value, if I'm not mistaken. Yes, both point to the same variable. Yes, this is not Dave. Wait, this is double. Oh lord. So yeah, that pretty much covers everything for us. we've seen reference, we've seen ownership and borrowing, which is why Rust is so safe. After we have seen the C and C++, now we are going to pointer in C day 5. As I said, in undefined behavior, we have 4 ways on how a language turns our source code into something that the CPU can execute. We have covered compiled languages, C and C++ and Rust. Now we have interpreted languages. The first one is purely interpreted. This is rare. As you can see, Python, Ruby, and PHP are not included in this list, as it's a very old one. We have discussed this earlier in our undefined behavior talk. The purely interpreted languages with your source code line by line and tell the CPU what to do. Whenever you assign a variable, the value lives on the interpreter's heap as your program is inside the interpreter bubble or sandbox. It's the interpreter's responsibility to free and allocate a memory for your variable, as the interpreter is usually written in C. Now we have a VM-based interpreted and bytecode. So now we are answering. This is the use case for like C, Python, or Ruby. Just as a side note, this example of Python is specifically created in C Python. So behavior may differ from language runtime to language runtime. But since the most used interpreter is the C Python, you should be fine. I don't know. So let's paste this one. This doesn't. So what you need to know about Python or Ruby is that everything is an object. This doesn't create a new box under the hood. It creates a pointer to a pre-existing object, which is immutable. This creates a pointer to the same object. This one doesn't change value. It points to an object. So this line, B is equal to A, means B now points to the same object as A. And at this line, B doesn't change the value of object 10, as integer object is immutable. Instead, it points to a new 8 object. So let's do, okay, hold on for a second, alright? Let me change the experiments. We go to pointer. Okay. We have this one. That's why. So that is why you can call a method on a variable using underscore function name, like this one. Func a dot underscore underscore add underscore underscore ad. This returns the value of a plus the input, which is 80, but it doesn't change the value of a, since a is a pointer to a 10 object and an integer is immutable. Now that's a different case for list. List creates a list or mutable array with the value of 1, 2, 3. Behind the scene, this creates a pointer to the x, or in other terms, a reference to x. So y and x points to the same value, 1, 2, and 3. So when we append another value to the list, x also changes as well. So let's, yeah, now we see it in action. Now where does the pointer comes in? It already is showed using the list, but the pointer comes in pre-allocation, insert strings, and explicit optimization. Oh lord, this is quite huge. So Python pre-allocate most used integer, which is from -5 to 256. So these both points to the same object value, which is integer -5. This will print true since they both point to the same value. Now this creates a new object 100, and this is not the Python compiler actually. This is the bytecode compiler if I'm not mistaken. And since this is close enough in one file, it points to the object 100. This creates a new object, and since this is close enough, the B will point to the same object as A. And this points to the same object. So both A, B, and C points to the same object. It must be noted that if the variable is a different .py file or a library, Python will certainly create a new object. Not certainly, but this is the most common case in the C Python in language runtime. Next, this is just a separator, and now we are entering the string. Creates a new string object with the value of hello world. Intern string. Since this is a simple string and has no special character, the string is intern and point to the same object. So hello and world points to the same hello world object. So when we do this, it returns true. And the address of, so we get the address using ID and converts it to a hex. We see that the address is same. Next, this creates a new object string as well. Since hello world is already created and is a literal, the compiler is smart. It optimizes. Pro is a pointer to the same object as new. It's the same. However, for runtime operation like string concatenating, this can be optimized by the bytecode compiler. So it creates two separate objects on the heap. And this is covering about the singleton, which is there's only one true, one false, and one none object in your entire program. Every true, false, and none points to the same non-true and false object. So let's run this one. Forget to save again. Yes, A, B, and C are the same. The hello world and hello world is the same. This is the same, and now this is false because it's a runtime operation, and the runtime creates a new object. Is true the same as true? Yes, this is proves what I said. Now we've talked about the interpreted VM-based interpreted languages by using Python as an example. Now we talk about just-in-time compile, which we will cover about Java and JavaScript. As we talk about in undefined behavior, just-in-time compile is similar to VM-based interpretation with only hotspot optimization. However, how they manage variable is different. For just-in-time compile, not everything is an object. Primitives like integer, float, char, the one with no capital usually, are separate, like C, C++, or Rust. Now the pointers comes in with, so let's go to Java. Everything is explained within this code, so let's deep dive into it. For primitives like integer, they don't create a pointer to pre-allocated value. It creates a new variable on the stack. Sorry. So the operand, the same value, equal value, operand if I'm not mistaken. For primitives, it checks whether the value is the same or not for primitives. Last one again. So this one, we have system out.println. We print the identity hash code. So identity hash code actually accepts an object. So this line, autobox raw integer into an integer object, which creates a new object on the array, on the heap. And after it's used, it removes the object. It's not immediately removed, but the garbage collector will handle that. Just like VM-based interpreted languages like Python. Java has pre-allocated integer object from -128 to -127. And as a side note, this does not return an address, instead a unique hash code. So Java has pre-allocated integer just like Python from -128 to 127. And identity hash code does not return an address. Instead, it returns a hash code, and it's not guaranteed to be unique, but you get the general idea of is a variable the same. So this time we create a new object on the heap, and it doesn't optimize like Python. This is a different object. Now this creates a reference to A, so both C and A points to the same 1,290 objects. So this will print, is A and B the same object? If not, prints no, and this will certainly be the same. It prints the ID. This is not certainly unique, I just forgot to change it, so yeah. So this line, it doesn't change the value of A. Instead, it creates a new object and points to the object of 1,890. So the value of A and C. Now if we have an operand, we have equal symbols is used to check whether the is the same object. Then how do we check if the value is the same? Using dot equals. Since this is an object, it has methods to check whether something is equal to it. We use a dot equals. So let's run this one. Java C or Java C? Java C. Pointer dot Java. Okay. Java. Sorry. Now x and y is the same. As I said, it's not the same. They are two separate objects. Now A and C is the same. The hash code for A and B is different. However, A and C is the same. Now the value of A is unchanged while C is changed. A and B has the same value but has different address. Now we go to JavaScript as a node, not node. For JavaScript, for safety reason, they do not expose functions like ID or is to get a way to know the memory address. However, among Python, Ruby, and Java, JavaScript, specifically the V8 runtime, which is maintained by Google, or Google's runtime of JavaScript, is the most aggressive as JS is so dynamic. We'll pass this into a pointer.js. JavaScript treats every number as a float by the IEEE 754 standard. Now, when you create a number for an integer variable in JavaScript, it doesn't store the address to the heap. It's not an object like Python or Java. Instead, it stores the binary of the value. So every number has a binary. You store the binary inside the variable, so you just need to convert it. This copies the binary to the y variable, and when we change the value, we do bitewise math to the binary, which is one of the cheapest performance things CPU can do. This prints 8, print 9. The runtime can just check whether the end of the binary is 0 for value or 1 for address. I don't really understand about this one deeply, but you store for small integers Smi inside this very variable. It has the binary of the binary of the value, and it has like some sort of unique some sort of identifier. 0 for the real value, 0 if it is a real value and you can just convert it directly into an integer, or 1 for if it is a pointer to object on the heap. And there are 7 primitives in JavaScript: number, string, boolean, big int, integer, symbol, null, and undefined. And primitives are immutable. So we have seen Smi for integer, but for string we have lie white pattern or the intern table. Now for every string it's put on the intern table. It doesn't recreate a new primitives. Instead, it just points to the same row of table. And when you do runtime operation of concatenating string, V8 doesn't create a new intern row inside the table. It just points to string A plus B. So when you do let hello world equals to hello and world, this doesn't store the combined string of hello and world. Instead, it just saves, oh, hello world. It points to both hello and world. So it's like a nested pointer or something. The last one is hidden classes and optimization. We have a type. This is for TypeScript thing. Since I don't use JavaScript, I use TypeScript instead. We have this function which returns the object.x time sum of object x and y. And this one, when we create this one, this creates a hidden classes for this object x with id 0 and id 1. So the next time the V8 doesn't have to go to this class and take takes the value of x. Instead, it can just go to the id 0, which is x, and get the value out. Just jumps directly into the object and goes to like, what's the id? Maybe id 56, and just skips the using the string. So instead, this one, the id has changed, the y and x, it's switched now. So this creates a new hidden classes. Note there are still pointers to an object on the heap with string, number, and etc. types with the capital, correct, but most of the time we use primitives. So how can primitive have methods if it is just a value on the heap or stack, sorry. This is a primitive, and for this to work, V8 does these three things. It wraps the primitive in an object on the heap, it performs the method, and immediately afterwards, after the method is done, it removes the object. So when we do this, this is a primitives, and for a split second, it was a object. So let's do node pointer dot yes. Yes, it prints everything correctly. So as a closing for this nearly 1 hour video, is it 1 hour already? Yes, 1 hour. Alright, I'm gonna have a blast uploading this. VM-based interpreter and JIT compiled use garbage collector. In a language where everything is shared and you don't know when a variable is free or not, this is where garbage collectors comes in. Most modern VMs use tracing garbage collection, where reachability, not reference count, determines the object lifetime. So you don't need to call malloc or free in a JavaScript or other programs. So as a side note, JavaScript V8 is the most complex thing I learned today, but this basically sums everything up for my pointer documentation. It's 7,000 words already, and it's 1 hour already. I learned these pointer things while I'm in the middle of an ELPG competition. Oh my god. But yeah, I guess that's pretty much it. I was supposed to go to raw SES calls, but I changed the plan after I realized something. Probably I'll dive deeper into memory first, stack, heap, and static, and how they're not actually available on the RAM. Instead, they're just something the OS and AB mixed up. AB, application binary interface. So yeah, that's pretty much it. I've yapped for hours, and now I'm Bernardus signing out.